schedule, um, I'm going to give you some homework that's already on Canvas for Chapter 5. Then we're going to go into Chapter 6 next week. And then we're going to have an exam over Chapters 1 through 6 after that. So that's why we need to keep moving. So let me find my notes. Hope this thing can hear me. Okay, so Chapter 5 talks about the analysis of beams. Up till now we've been doing different formulas and trying to understand, trigonometry and all that stuff, and how loads are transmitted, etc. And so everything kind of builds on everything else. And then we studied trusses a little bit and how the loads are distributed through the members of the truss. And now we're into beams. And remember that a beam is a structural member resting on supports at its ends. So, that's pretty simple. There's beams holding up this floor that are resting on columns, usually. Beams tend to bend rather than lengthen. A column will lengthen or shorten. It'll be in tension or compression. And a beam will tend to bend. Of course, there is some tension and compression in that bending, but overall, we just say that it bends. It doesn't shorten or lengthen. The forces that a beam is required to resist are the downward loads and the upward supporting forces, which are called what? You remember? Reactions! You get a star. Okay. So you got the downward load here, and then you got the reaction. Whoops, there. Caitlin, does that? Okay. I guess I need to make it. So the upward supporting forces are called reactions. There are several types of beams, and I've drawn them here. We've got the simple beam right there, which is just, you got your reactions, the upward supporting forces, and you got a downward force. It's just a simple beam, and those tend to behave like this. The reactions are pushing it up, and your force is pushing it down, so it's bending. Then you've got a cantilevered situation right here, where you've got a rigid force over here. The beam is sticking out, cantilevered, and you've got a force that's making it bend down. Then you have an overhanging beam, which is also kind of like a cantilevered beam. You got reactions here. You've got forces coming down, and you've got a force coming down where there's nothing to hold it. So those tend to come up and down. You got, it's supporting it there, then it bends down, then it goes back up, and then of course these are exaggerated. You don't really see those forces, but that's what you're fighting against when you design it and you're putting the steel in there to make it stay rigid. So that would be an overhanging beam. These are important. You need to remember these. Then you got continuous, which has supports at both ends and sometimes in the middle. And you got loads on the top. And those behave like they just go up and down forever and ever. Then you have restrained, where it's rigid in both ends, it's stuck in a wall or something, and you got a force coming down. And that would tend to act like that, where it would just bend down in the middle. So does everybody understand? You got how many types? You've got simple, cantilevered, overhanging, continuous, and restrained, and that's in your book as well. Any questions on that? Pretty easy. Okay. Loads on beams can be classified as concentrated or distributed. Concentrated loads are like these shown here with the arrows, or the simple beam up here. It's a concentrated load. In real life, a concentrated load would be, let's see, where a column may rest on the foundation. That's a concentrated load on that area. Or if there's a heavy object that you're planning for, you know, like you got a great big safe or something that's going to be on a floor, that can be probably considered a concentrated load. It's just going to be heavy on that spot. Distributed loads are uniformly distributed. And that's kind of what engineers deal with a lot more, I think. I mean, there's concentrated loads and distributed loads, but a distributed load, as I've shown here, you have your columns in your structure, and then you've got your beams, your girders and your beams are these lines. Then, for instance, in this room, they may design it for 100 pounds per square foot live load. That's a distributed load. Anywhere, people could be walking there, it could be 100 pounds per square foot. So they have to design it for that. So this distributed load, you got a beam here, you got a beam here, and you got a beam here. So this 100 pounds per square foot has to take care of this shaded area right here. So when you draw your diagram for that, and I'm looking sideways so I can line it up, you've got your beam, and then they've drawn their distributed load at 100 pounds per square foot. And when you calculate your moments and things like that, sometimes you turn that into, just for your calculation purposes, you know, that was 10 feet long, and that's 100 pounds per foot. That would be 10 times 100 pounds, and about in the middle. So everybody get that? Distributed loads? Distributed loads can be uneven sometimes, but more usually they are even. Is there any questions on that? Nope. Okay. Loads produce stresses in beams called moment and shear. So, do you know what does a moment do? Tends to rotate. And what does shear do? Anybody know? Eventually. The shear is more of a vertical force, which what makes it want to slip past the other thing, or whatever's there. Moment is a rotation or a bending. So those are the most common stresses that you have to design against. Shear has a tendency to want to slice, like you said, and break it off. Moment causes the bending. The magnitude of the vertical shear at any section of a beam is equal to the algebraic sum of all the vertical forces on one side of the beam. So that was repeated several times in the book. The magnitude of the vertical shear at any section of a beam is equal to the algebraic sum of all the vertical forces on one side of the section. So you can, basically it's shear equals reaction minus loads. And we'll go through some problems in a minute, but you know, basically if you're drawing a shear diagram, which I'll draw in a few minutes, your shear is going to, like if you could slice the beam in half, your shear is going to take into account all the loads on that side, and then on that side it'll go to the right or to the left. The reason that we are concerned about shear is because the greatest tendency for a beam to fail by bending is at the section of the beam where the value of shear is 0. So we need to figure out where that value is, because that's where the beam needs to be the strongest. So then I'm going to show you some shear diagramming. So this is a simple beam. So your shear diagram is, you would draw a graphical representation of your beam, something like that. And then, you know, to scale, whatever scale you use on your graph paper, you want to go, your first load is right here, so that, remember what, oh, why did I do that? So you're going to go up, you know, graphical representation of 9, you know, 9 squares, 9½ inches, I don't know, whatever your scale is. So it's plus 9. Then your next load is 8 feet over, so you're gonna, it's just gonna be straight until you get to that point. And then you've got 15 kips going down, so you're gonna go down to 15. You're slicing down. You get that? So then this line goes down 15 units, whatever your units are. Then you're just, since it's, that's the only load, you're going to go back over to the end, and then you're going to go up your 6, and it should end there. So there's your shear diagram. It's pretty simple, right? So, and that's just for a simple load. For a concentrated load, which is this one, evenly distributed load, draw your line. Then here you've got a reaction that goes straight up for 36 kips. So you're going to, you know, scale that up for 36, whatever that's going to be. Then you know that this time the load is evenly distributed. So it's going to angle downward instead of going straight across because we have this load going right there. But what you've got to do is figure out the load, which is 4 kips per foot times 18. So what does that whole load equal to? Somebody multiply that out. 4 kips times 18 feet equals 72 kips. So eventually we got to go down 72 until we get over here. So you measure, and this is out of scale because it's hard to scale on this thing, but you measure down, it's going to be where this load is. You're going to go down to 36, then you have an angle. That's your shear, and that's the moment where shear equals 0. That's not exactly drawn to scale, but so you go up 36 and down 36. That's your evenly distributed load, or your uniform load. That's what the shear diagram equals, and that's where the bending moment is going to be the greatest, and we'll go over that in a minute, is at where the shear equals 0. Does that make sense?
That one was concentrated?
Concentrated, you're right. Uniform, concentrated. Okay? So the next one you have, you got several different loads on there. I should have had more space between these. But, so you're going to draw your line, or your graphical representation. You're going to go up 7. Then you're going to go over 4. This one doesn't have a concentrated load. But then you're going to go, oops. Then you're going to go down 6. Why is it doing that?
Because it thinks that you're clicking on the end of that first line. So draw your line, and then start on the bottom and go up. There you go.
Okay. Then you're going to go over 4 more feet. And then now it's going to go straight down 9, or whatever your scale is. And then you're going to go to where the next load is, and then you can come up 8, and it should end there. So that's your shear diagram for that. It's not drawn very well, but make sense? there, you're at 1 here,
Do
you're
we
at,
always start on the left side?
conventionally, I don't know that you have to, but just conventional way. Um, I don't see why it would make a difference, do you?
Well, I mean, if you flipped it over, it would, if you started on the 8 and you went up,
Oh, well, your
9.
shear would still be, what we're looking for is where it crosses 0.
Oh, okay,
So that would still be the same, right? Yeah,
yeah,
so, I mean, that's the whole purpose of drawing them,
okay,
so,
so it doesn't matter.
no. Okay, and then you get, for a combined uniform and point load, you would have something like this. So a little more space. Okay, now what's it doing? Draw your beam. And so what's gonna happen at this end?
Gonna go up 26,
Right, so we're gonna go up 26. Then what do you think we're gonna do?
go over to where the 20K is.
Well, eventually, but not quite, because we gotta take into account this distributed load, and that starts before the 20K. So, remember the distributed load, looks like that. So, it's an angle, so we have to figure that out. So, first of all, let's figure out how much this is. It is 6 tips times, what happened to my number? I had numbers in there earlier, I swear.
It's not there now.
Okay, this is 4 feet. This is 2 feet, even though it's not drawn to scale. This is another 2 feet, and this is 4 feet. So that's 8 feet of 6 kips times 6 kips per foot equals what?
48.
48, that's right. So, all right. So we got 48, and that's gonna act, I should write that correctly. It's gonna act in the middle of that load, or that's where you're gonna think about it. So that would be at the 4 foot mark, right? So we can draw that 48 kind of there, just for our thinking purposes. But this portion, we gotta take into account, let me go through this. Do 48, okay. So our shear is gonna go to this point, it's gonna be straight, because that's what it thinks is happening. So right there, it's gonna start sloping down, until we get to that 20K, when it's gonna go down hard. So first we gotta think of this distributed load, I guess, before we think of all of it. And that's just 2 feet times 6, which is what, 12?
Well,
So this little section here is 12. So then we'll drop down, we'll angle down 12 until we hit this line. So we get about even with that. And then, I'll say that equals minus 12. Then we're gonna go, because there is a point load there, we're gonna go straight down 20, right? Y'all agree? Stop it!
start from the bottom and go up.
Okay. We're gonna go straight down, 6 times 6 is 36. And that will go to our load over here. And we'll angle down that distance times 36. So that's minus 36. And then this is plus 42. And that's your moment, your shear equals 0. Does that make sense? Any questions?
So when we do the, plus 42 from 36, okay.
Yeah. Now when you draw these on your homework, you're going to draw these diagrams and try to draw them to some sort of scale. Is it showing on your screen?
On graph paper,
Yeah, you should.
or can we draw them on AutoCAD?
Well, I think you tend to be too exact with AutoCAD. So, I mean, I would do them on graph paper. I tried to, the homework, I mean, you may not want to do it on the sheet the PDF that's on the Canvas, but you may want to redraw them on graph paper to scale. I don't think you need to do it on AutoCAD, but if you just want to be that way, you can. It's easier? Okay.
Because then I just print it onto PDF and then submit my answers.
That's fine. As long as it's a PDF, then I can, because sometimes I can't, if I don't have AutoCAD on wherever I'm working, I can't see it.
Yeah.
So does that make sense, shear diagramming? Okay, so, shear equals the reaction minus the loads. That's what you got to remember. So the moment of a force is the tendency of a force to cause rotation about a certain point or axis. We discussed that earlier. The bending moment at any section of the beam is equal to the algebraic sum of all the moments of the forces on that side of the section, similar to shear. When we design a beam, we are concerned with the maximum value of the bending moment, and this always occurs where shear equals 0. So all of these beams where the shear across the line is what the maximum bending moment is. And that's what we care about, because that's where the beam needs to be the strongest. So now we'll go back on these and we'll show the moment. And probably, let's see. Go to this. Let's see if I'll do this a different color, if I can figure that out. That in red. Okay. So, a moment diagram on a concentrated load. Where's the moment going to be the most? At 0, where the shear equals 0. So you can overlay your moment diagram if you want on your shear diagram, or you can draw it below it. It's up to you. So the moment is going to actually be equal to the area of the shear. And that's an easy way to figure it out. So this area here is plus 9, and it's 8 feet long. So what does that equal? 8 times 9. So on our thing, we have to go up, this is way out of scale, but we'll measure up 72, and it's going to just be a straight line up there. That's your maximum moment right there. Then, what's the area down here? It's 12 times 6. Right? So that should be, that's the same thing, right? So then we're going to go back down to there. gonna equal the area of this, the maximum moment, right there. So you would say, how do you figure out the area of a triangle? You may remember?
1/2 of length times, or 1/2 of base. I know it's 1/2 of something.
Well, it's basically, if you turn it into a rectangle, then it's half of that.
It's 1/2 of base times height. Because if you turn it into,
Yeah,
if you turn it into a square, it would be your base
Right.
and your height. So yeah, 1/2 of b times.
right. So this is 36, that's 9 feet, right there. So it's, the area of that is gonna be 1/2 times the base, which is 9, times 36. So what does that equal?
$162.
162. So we know that our maximum moment, if we did it to scale, is gonna be up here somewhere at 162 above the line. 162. And then to get to that on a uniform distributed load, it's a parabola, which is a shape that's, you don't have to be too exact for our purposes, but that's what it looks like.
So if you're doing it on AutoCAD, you just use.
That's right. Yours can be exact, and I will grade yours as such. So, that's what your moment diagram looks for, a simply uniformly distributed load. So that equals, if you figured all that out, it would, that point there equals, right, the area of that. That's how you get to the maximum moment. For this one, find out where that is. Okay, this does not have a uniformly distributed load, so the lines between the different magnitudes of moment are going to be straight. So the first point, and we know the maximum moment's going to be at this point up here somewhere, wherever that is. But to get to that point, we have to say that the first one over here, I think it's so sensitive. What's the area of this? It's going to be 4 times 7, which is 4 times 7 equals 28, right? So you're going to go from, at this point, you're going to line it up with there, you're going to go up.
Every time you click undo, yeah, you just need to tap somewhere on the side.
Okay. I might have to do that over. That's 28. So you're going to go 28. Whatever.
I think it's doing that because you're using that precision instead of just a regular marker.
Maybe that's okay. So then your moment line overlaying the shear is going to go up to 28 above, this line meaning 0. Then your next point is going to be over here somewhere, and you're going to add the area in this section, which is 1 times 4. It's 4, right? So you're going to go up another 4 straight line up to 28, then you go over, because this equals 4, you're going to go over and up 4 and 1, and then you go down. Make sense? Now we got the combined one. Give it all one.
What was that one?
The one we just did?
Mhm.
It was a uniform, no, it was just several different concentrated loads. This one has a uniformly distributed load and a concentrated load. So we already did our shear. So this one we're going to have a combination of curved lines and straight lines. But the first thing we want to notice is from here to here, to this point, this green line shows where the curved line is going to start, and over here it's going to be straight, because here we have our distributed load, and that's always a parabolic line. Back to our moment diagram. For this first section, it's going to be equal to the 26 times 4, this area here, which equals 104. So you're going to go up in a straight line. You're going to measure up to 104, wherever that might be, and that's going to be a straight line. That's 104. How'd you do that?
Maybe your thing finished recording?
It's not recording anymore? Yeah, it's recording. I think it is. I think I just hit something. I hope it's recording, or Diego loses out. Okay, so that's 104. Okay. Then you have the beginning of your evenly distributed load, and the maximum moment occurs at the point of zero shear, which is right there. So you've got 26 plus, let's see, what do we got to do? We got to figure out that area of the triangle. So it's 26 plus, this point here is 14, I believe. 26 minus 12 is 14. So you got 26 plus 14 divided by 2 times 2. Wait, I gotta figure this out.
Wouldn't our base, our height be 12 and our base be 2?
But we also got to figure out, this whole area, and that would be that area and that area, right? So you have 2, this is 2 feet wide, right? And that's 14 feet, so that's
For
26.
the area of that rectangle, you would do 14 times 2 because
Yes.
it's 2 feet wide, right?
Yeah,
So 2 times 14 would give you the area of that. That's
Right.
going to be 28.
right.
And then the area of the triangle is going to be, because you're coming down 12, 12 times 2 divided in half. So it'd be 12 again.
Right. So 12 and 28 is what? 40, right? So we're gonna go up another 40. But this is where it's gonna start being a curve. So you met, it's totally out of scale, but measure up to 40 there, and then for 3, it's gonna be, basically you're gonna end up back over here. I mean, for this section over here, so you start your curve there because of the distributed load, and then you have, you're gonna curve back down to that point. And that, 6 times 2. So that's, you're gonna come back down about another 144 or whatever it is, I think. Yeah. 104 plus, wait,
Maybe 148.
104 plus 40 is 144. So that point there is 144. Right? And then you gotta get back down to here, so then that should equal, those two areas. We can double check that. That's minus 20 times 6 is, 120, right? No, what's 20 times 6? Yeah, 120. 120. And that's 36 and 20.
The area of that triangle would be 756.
Really? It would be 36 times
Oh, wait, no. It
42
would be
divided by
42 times 6. I'm sorry, I did that. 42 times 6
divided by 2.
divided by 2. Be 126.
This one down here?
Yeah. That one above you, the 120, I don't. It'd be 6 times 6. Because you still have 14 on that 20K. You still have 14 to get to your baseline, and then
Oh.
6 more to go down, and then you're going across 6. So 6 times 6.
You're right.
So that base would be 36. Add 36 to 126. 162.
That doesn't add up to, right? So we came down in the shear diagram. It's minus
Oh,
20.
I see where we're messing
Is
up.
it the area of the little triangle?
The area of the triangle on the bottom is not 42 times 6, it's 36 times 6.
Well, it's not that equal, because we already went down.
So it would be 108 plus, because we're doing a total of 42.
But that's from there to there, so we
Yeah,
gotta take
but
off that part.
We have to take off those 6 inches.
Okay.
So it's 42 minus 6. Right here where you have a 42, it would be 42 minus 6. And that would give you 36 times the 6 feet across, and well, 1/2 of that times 6.
Divided by 2.
Yeah. And that would give you the area of that. Read it to you. Is 108. So right there where we have 126, that's actually 108.
What did we say this was?
36. So 108 plus 36.
That equals 144, right?
44.
So we're good. Okay. That was all. So I think this is a little bit simpler than the way the book kind of did it, but because you do your shear diagram first, and then because then then you can use the area of the shear to the left or to the right of that to figure out the moment. And then you know that if it's a distributed lobe, it's gonna be sort of, kind of a curve, and if it's uh, just a point lobe, then it's gonna be a straight line. So, the other, thing to remember on these is that the inflection point is where the moment passes through zero. So sometimes, I don't think all of these didn't, sometimes the moment can pass through, you can have a moment diagram that would look, it might have something like that, and then it might go down, and then it might go up. And these would be the inflection points. And that's gonna be the point where, it changes from compression to tension. And the engineer needs to understand that, because that's also a point where there's gonna be a lot of stress. So in shear diagrams, the vertical distance represents the force and the horizontal represents the length. The magnitude of the bending moment at any section of the beam is equal to the area of the shear diagram to the left of the section. That's what we went through there. Is there any questions? I didn't use homework from the book on this. I used some other problems that I think are simpler. So, but right now I want you to go through and take that quiz in the time remaining on terminology, and then you can do this homework before next time, before Tuesday. It's due Tuesday. I don't think it'll be too difficult. And then I'll probably launch a discussion on Tuesday concerning chapter 6, which is more about this stuff. Okay? And if you need to get caught up on your other stuff, you can see how it all kind of builds. So, anyway, let me turn this off.